In this lecture, we will learn about central limit theorem and its relevance to business. Let's start with a small example. There is a process where letter of credit is being issued by a bank and the banking officer is collecting data. He is collecting data in the following manner. He is collecting 51 samples every day, and like that he is collected data for 50 days. So all put together he would have 2550 data points. Let's see how this data looks like. So here is this data. Each row here is a day's data and the 51 samples of a given day are stacked one next to each other. So what I'm going to do is I want to find out what kind of pattern this data has. So I'm going to do a probability plot, a distribution for this. For me to do the distribution, I have to stack up this data. So I have, for simplicity, already stacked up this data. By stacking up, I mean that I have grouped all this data one below the other in a single column so that we can give this column to Minitab and Minitab can give us the distribution. So let's go to stat, basic statistics, and I'm going to click on graphical summary. I'm going to go to the cell in which this data is there and I'm going to say OK. And now I look at this distribution. This distribution is skewed. The Anderson-Darling coefficient is very high and the p-value is very low, which means that this distribution is not normal at all. It has a mean of 0.75 and a standard deviation of 0.44. So from my current experience, I can at least conclude that this looks like a viable distribution and I need to fit this data into a viable distribution. But wait, before we start doing that, let's do one small experiment. I go back to this data and I want to find out what is the daily average, which means I have taken average of all the samples of a given day and I have put it in here. So this cell 0.776527 represents the average of the first day, and likewise I have collected averages of all the days, or rather I have computed the average of all the days. Let me now go and plot a distribution for this. So I go to graphical summary and I click on daily average and I have a distribution here. This distribution has a very low Anderson-Darling coefficient and the p-value is greater than 0.05. Visually the distribution looks perfectly normal. So I'm now puzzled that the parent data looked non-normal. It was skewed and I thought it was a viable distribution, but the sample data, that is the daily sample data, is in fact normal. If you look at the average is exactly same as the average that we got with the entire population. So the mean is equal to the mean of the means, which is equal to 0.75116. So with that observation, I will go and continue my experiment. This time what I'm going to do is, instead of collecting, let's say 51 samples, I collected only 3 samples every day. So let's say I collected only 1 sample in the morning, 1 in the afternoon and 1 towards the evening. So I had 3 samples. So the average of all the 3 values is what I am showing you here for simplicity. So let's go and plot a distribution for this. If you look at this data, and if I'm going to put this next to what we got for 51 samples, you would find that when the samples are lesser, the distribution is not symmetrical. But as I increase the sample size, the distribution tends to be more and more normal. Is that correct? In fact, this distribution is having a p-value less than 0.05. So it is not normal, but it's much more better than my original source data. So what is the inference from this? So the inference is that immaterial of my original distribution, the average of the samples tends to be a normal distribution. So whatever might be my original distribution, if you take the average of the samples and then plot a distribution of that data, that will be a normal distribution. That is my first inference. Two other things that I want to note here is that as the sample size increases, the distributions become more and more normal and the spread or the variation in the distribution to be decreasing. This is exactly what is characterized by central limit theorem. Central limit theorem states that immaterial of what your original distribution is, if you take sample data and do a distribution of that sample data, that distribution would be normal and it would have a mean same as the mean of the population, which means the sample mean is same as the mean of the population. We saw that in the data. The standard deviation of the sample mean, that is from the sample distribution, would be equal to standard deviation of the population divided by square root of sample size. So I am just repeating this again in our own example. The standard deviation of the sample with 51 samples would be equal to the standard deviation of my population divided by square root of 51, because I collected 51 samples every day. This parameter, standard deviation of the sample mean, is also commonly called in statistics as standard error of the mean or SE. This represents the error in the mean. In other words, you would expect the mean to vary between these limits. The variation for the mean is characterized by this formula. So let's do this experiment one more time. We did for 51 samples and we did for 3 samples. But out of curiosity, I want to know what happens when my sample size is 30. So I have the data for 30 samples and I want to see how that distribution looks like. So here is my data. I have the daily average for 30 samples collected for all the 50 days. I would go and plot the distribution for that now. And I find that the distribution is actually normal now. So for 3 samples it was not normal. For 30 samples it is normal. So what does that mean? It means that around 30 samples the magic usually starts to happen. As you start increasing your sample size, when the sample size hits a threshold which is around 30 and not exactly 30, the sample distribution becomes normal. So that means that immaterial of what my original distribution is, if I'm able to collect sample data and if I'm able to make sure that the number of samples that I have is around 30, then I could analyze the sample averages and draw a lot of conclusion about the original parent distribution without really knowing what that parent distribution itself is.